Yeah, in the earlier lectures we have seen how magnetic materials can be used in different applications. Whenever we talk about magnetic materials, the most important feature that comes to our mind is magnets, and the fundamental applications that govern magnets and how the magnetic induction can be used in variety of applications. As we have seen in the previous lectures, magnetic materials also play a decisive role in controlling other properties. For example, in the case of manganites, we said magnetic property of manganites controls the electrical conductivity, and two dual properties go hand in hand, which we call it as a dual property of magnetoresistance, where magnetism governs the resistivity of that material. And we have also seen how this effect is pronounced in multilayers, and we were talking about tunneling magnetoresistance. Also, as another example, we showed how we can translate a insulating or a semiconducting material by carefully doping some magnetic impurity, how you can transform even with low level of doping, say 1 or 2%, you can still transform that material to go magnetic. Today I am going to isolate another important group of materials called magnetic materials that retains shape. So, no matter what happens to this material, because of its intrinsic property of this magnetic material to get deformed from a elastic to a super elastic behavior, they have a special tendency to retain its memory. So, when a particular stimuli is given, it can come back to its original shape. So, this is pronounced in a rather few materials, predominantly they are called alloys, and these alloys are materials sandwiched between few 3D and 4D metals, and there are also non-metallic materials called polymers, which show the same property, that is to retain its shape. So, I will take you through some issues, and more so I will also highlight especially one aspect of this magnetic material, that is magnetic alloys, which is finding lot of applications in today's life. To start with, let us go with some of the basic definitions. Shape memory materials, they are classified as SMMs. So, shape memory materials are featured by their ability to recover their original shape from a significant and seemingly plastic deformation. You can just pull it, and after a particular stimuli it can come back to its same shape. And this stimuli can be either pressure, or it can be temperature, or it can be light, and so on. This is known as shape memory effect, which we call it as SME. In alloys, it is usually superplasticity that is happening. Even in some oxides, you can actually pull such oxides at a particular temperature and it almost behaves like rubber, and it can even go through a plastic deformation. So, they are called super elasticity, and this is more pronounced in metals or alloys, and in polymers it is called viscoelasticity. It can go beyond its blending temperature, and these are observed at certain conditions. The SME can be utilized in many fields, for example in aerospace engineering, in deployable structures and morphing wings, mainly to arrest the vibrations in aerodynamics. These alloys are specially used, and if you go to medical devices, as an extreme case, you even see in stents that are deployed in our cardiovascular system, you can see these are finding enormous application. A recent article in Materials World, which was written by Huang and co-workers, they have specially covered some of the essential features of this of these alloys. I would like to emphasize more with respect to this article and pick out some of the examples which they have listed out. So, I will be essentially dealing with this article written by Huang, and this is the article that featured in Materials World. So, as I told you, the severely and quasi plastically distorted materials, they recover to their original shape at the presence of a right stimulus. So, there are 2-3 group of compounds which we will be studying in today's lecture. One is superplastic or shape memory alloys, the next one is shape memory polymers, and we will also show some example of shape memory hybrids that has both the polymer and the alloys impregnated in each other. Therefore, we can see how the properties can be understood. As I told you in the beginning, shape memory alloys are thermoresponsive. So, at low temperature, suppose you try to make a particular shape like a spring or a hook using alloy, then at a high temperature you can actually remove that shape at the transition temperature or at the temperature where there is a martensitic transformation of this alloy, and once you cool it down, again the same shape that you formed for this alloy can be retained. So, this is called thermoresponsive. The shape recovery is heat. Some shape memory alloys also show magneto response. In other words, applying a field, you can try to revert it back to the same shape. Shape memory alloys can be categorized into many compounds. Just single out some of the widely used ones in today's application. Nickel titanium alloy is one of the predominantly used one, and this was a path breaking discovery by US Defense Lab in the early late part of the last century, and it is also nicknamed as nitinol nickel titanium alloy, and the essential feature is it has very high performance in terms of elasticity, mechanical strength, and also it has a very good biocompatibility, closely followed by copper based alloys. And for example, copper based alloys are CuAlNi and CuZnAl. These are very good compounds which are cost effective, because unlike nickel and titanium, copper based alloys are much more cheaper, and processing is easier because they are more malleable. So, you can the workability into different shapes is achieved much better for copper based alloys. We also have ferrous based SMAs, that is shape memory alloys, which have very high tensile strength and huge super elasticity. So, in today's application you see almost either of this group of alloys competing for the market, and one of the most recent application of this shape memory alloys is in the field of MEMS, micro electromechanical systems, which is used for device applications. It is one of the emerging field, and it is called MEMS technology. Lot of groups are actually converging into this area. Chemists, physicists and mechanical engineers are particularly interested in MEMS technology, because you can actually transcend from micron based devices into nano based devices, especially in constructing new MEMS device structures. One of the thing that is very important in a shape memory alloy is the transition that takes place. in nickel titanium alloys they are more expensive, but then they have a very good transformation to show this shape memory behavior, especially in the conversion of martensite to austenite or austenite to martensite transformation. And this figure shows the transformation ratio eta in terms of temperature. So as you start heating from the martensite which is stable at low temperature, the material actually transforms, and the transformation starts somewhere here, which we call it the starting point of austenite, and then at a particular temperature there is a complete conversion of this austenite to from martensite to austenite. And once you are here, you can actually cool this to the martensite by periodic cooling, and you can see here the martensite starts appearing again at temperature somewhere here, and then again the conversion is completely through when you go to MF, that is final state of martensite. So in this transformation from martensite to austenite and austenite to martensite, you essentially evolve with the hysteresis, and this is the hysteresis which makes this a useful shape memory alloy, which means at low temperature you stabilize the martensite phase, at high temperature you stabilize the austenite phase, and this is a plastic deformation that occurs in this alloy. So this is very important, and these alloys can also go through this martensite to austenite transformation, not necessarily with respect to temperature, but also with respect to stress, that is pressure. So you can also apply just pressure without temperature at a particular isothermal condition, you can bring about this phase transformation. Okay. So nitinol wire in terms of application is used in robotics because of the shape memory property. You can actually design robotic instruments using nitinol wire, that is why it is very costly, because you can actually use it for many functional applications. For example, the hobbyist robot Stickito is particularly made of nitinol wire, and in few magic tricks and particularly those involving heat and shape shifting. So it is for a layman it appears like it is a magic, but actually the property that is used is a shape memory alloy, therefore it is used in toys and in robotics, but this is not as cheap as that. This finds very sophisticated application. For example, Japanese Airlines Nippon developed this shape memory alloy that actually reduces aircraft's engine noise. Therefore, in several application in today's airline fabrication, nitinol is quite widely used. Another example is the prevalence of dental braces which we use to restructure our teeth using shape memory technology, because it will exert a constant tooth moving forces on the teeth, and therefore it always keeps the shape intact, and therefore this can be used as a dental braces, and also this has been used for several other dental applications. Now there are two ways this shape memory alloys can be used. They exhibit two sort of properties. Number one, it is a one way shape memory effect, I can call it, I can abbreviate this as SME, one way shape memory effect, or it can be a two way shape memory effect. What does it mean? Suppose this is the initial state and then I try to cool it. On cooling I want to bend this stuff, so it retains this shape, and I can play around with that, but once I do not want this shape I can actually heat it back and then I recover back the original shape which is nothing but your A. So, this is one way effect, which means whenever I go back, then at low temperature it will recognize this shape and it will form to this particular shape. So, it is one way, but at high temperature it again comes back to its original shape, but whenever I cool it at to low temperature, then it recognizes the shape that it was initially taken to. So, it will bend when it goes to that particular temperature. 2 SME is something different. You start with this structure and then in cold condition probably you have twisted it like this, and in hot condition you have actually twisted it like this. So, it will actually display both this property. Whenever you are in the cold temperature regime, then it will recognize this shape. When you come back to high temperature regime, it will recognize this shape. So, it is called a 2 SME space shape memory. So, both these effects are seen in a variety of compounds. Some show only one way, some show two way shape memory effect. So, we have a list of alloys which have been used. In the initial days of discovery, actually in the previous century, it was actually silver and gold based ones which have shown such a shape memory effect. But what we see now is predominantly the titanium nickel based one, which is nitinol, and the copper based ones and the iron based compounds. So, these have taken more limelight in the recent past because of its extraordinary stress strain characteristics, and also the way you can maneuver or you can make different value added products out of these alloys. I will show some of the examples in this talk. Let us take for example nitinol as a case study and see why nitinol can be used, and if nitinol is a shape memory alloy, then what are the characteristics of this. So, physical properties of nitinol, it has a density of 6.5 grams per cc, melting point is very high, therefore you can actually use this in variety of applications including aircraft because the melting temperature is quite high, and it does not change much over a wide spectrum of application. Whether it is high temperature or low temperature, the resistivity is of the order of micro ohms and it does not change much. Therefore, that serves as advantage that you can use this for applications. For joule heating, for example, I will show some examples how this super shape memory alloys can be used to regain its shape in using temperature. So, for joule heating, if you have resistivity along the same region at different temperature regimes, then it becomes very advantageous, and heat capacity is of 0.077 cals per gram, and then magnetic susceptibility, although it is low, but they are quite comparable again at high temperature and low temperature. They show magnetic property of the order of micro EMU per gram. Mechanical properties are also equally important when we are considering applications. Therefore, some of the values that we can have in mind, typical yield strength is 550 megapascal and 100 megapascal at low temperature. Then tensile strength ranges from 754 to 960 megapascal, because when you are trying to use pressure to induce shape, then you need to know what is the tensile strength that it can take. Otherwise, if you exceed the strength, tensile strength, then it will break, it will get totally deformed. Therefore, you should know under what tensile strength this shape memory alloy effect can be used. And similarly, you have the elastic modulus at low temperature and high temperature, which is 75 and 28 gigapascal. So, this is quite a good amount of details which can help us devise nitinol for several device applications. The most important property of this shape memory alloy is biocompatibility if we want to think about biological applications. One of the usefulness is the biocompatibility and strength properties of nitinol is to use this in switches and also as a stent material. Nowadays we have switchers, switcher materials which are both biodissolvable. So, you do not go back to the physician and try to cut open your switches after your wound is healed. You try to take this switcher out. You do not do that because nowadays you have a biodissolvable, it just dissolves over a period of time. So, you do not have the pain of going and removing your switcher through a physician. But nitinol is now used more so in as a stent material. Stent is nothing but a coiled wire like this. You can see the shape of this wire, and this is predominantly used in your cardiovascular applications. Also this sort of stents can be used in the neck region if there is a clot, in brain if there is a clot, then you can try to put a stent and then relieve the blood clot. You can also put this in kidney. Suppose there is a stone formation, then you can actually dilate that place by putting a stent, then the tract can be released. So, there are variety of applications for using stent, not just for coronary artery applications, but I will try to show you just one compound which has a good compromise on biocompatibility, mechanical strength, chemical properties, how this can be used for a very invasive procedure that is happening routinely in today's life. This is a cartoon that shows before and after how this nitinol based stent is employed. This is the one of the artery of our human heart, and this is a coronary artery where this yellow region what you see is nothing but your cholesterol deposit, which we call it as plaque, and this plaque can actually hinder the lumen flow. As a result, you get into myocardial infarction, which is your heart attack, in other words. So, if you go through this anginal problem, the best solution is to put a stent material inside to relieve this strain, and also to keep this plaque away so that the blood flow can be restored. So, this is the situation when you just insert the stent, and you can actually deploy the stent and try to restrain this by blowing it with a balloon, and that is what you see here. It is now stationed in the place where the blockage is, and once you station this stent, then the normal recovery of blood flow is established. As a result, a patient recovers from anginal problem. Now, the material that is placed here is nothing but a nitinol stent. It can also be replaced by several other stents. I will show you some example of that. What makes this nitinol more special, apart from the shape memory effect and the super elasticity, there are other features which makes nitinol more versatile, and they have amazing features. One is the stress hysteresis, which is considered to be rarest of the nitinol alloys. What it means is, although stress is elevated in a linear fashion whenever pressure is applied, for most of the materials that is the way, stress increases with pressure. But what happens in nitinol is something different. It actually exhibits a property called loading plateau, meaning a very small elevation of stress despite large application of pressure is achieved. So, even when you are pumping lot of pressure, the stress loading is very gradual. In other words, it does not go linearly, it rather tapers down, there is a loading plateau. As a result, suppose you insert your nitinol stent into the cardiovascular stuff, it does not really blow the coronary artery because it has a loading plateau. So, this is called a stress hysteresis, which is a very important feature of nitinol. And the second important feature is the elastic hysteresis. Elastic hysteresis is nothing but the tendency of the opening force to stay low despite the significant deflections of the stent. So, when you are trying to open the stent there, the opening force is actually very slow. If it is very sensitive and just deploys on its own, then you cannot even station your stent at the right position, because it would have got deployed somewhere else other than the place where you want. So, this is called elastic hysteresis, which is very useful and makes it more selective for housing a stent at the right position. So, another useful thing is the full compressibility that is shown by nitinol, meaning it has the ability to revert back to its original shape when external pressure which deforms it is released. So, this can also be a useful feature. Full compressibility is possible, like in some of the shape memory alloys, when you try to bring it back to the original shape, it will actually collapse only 90% or 80%. So, in such cases the usefulness of that material is lost because you do not regain the shape fully, but full compressibility is possible with nitinol, meaning by mistake a physician has deployed the stent for some purpose and he wants to collapse it back, it should actually go back 100%, otherwise that stent becomes useless. So, nitinol has full compressibility factor. It is yeah, so it is observed that stent can recover once the pressure is released, and it is also ferromagnetic with a reduced susceptibility to magnetic force. See, suppose the stent is deployed in the heart, the person will be very sensitive to magnetic field. So, if it is too sensitive, then that also can really bring about damage to the stented cardiovascular system. Therefore, it has to be ferromagnetic, but with the reduced susceptibility, which can help the patient from getting exposed to severe magnetic fields. So, these are some of the main characteristics of the nitinol which makes it special. So, in essence, shape memory alloys are super elastic in its application, but added to that comes two advantages. One is stress hysteresis and elastic hysteresis, and this along with the full compressibility factor makes nitinol one of the best ones. So, just to sum up why nitinol is good, if you look at the stress strain characteristics, you plot stress versus strain, and in different regime, this is how it works. In the high temperature state, you can see that if you take it beyond the transformation temperature, it does not come back, it is irreversible. Otherwise, within the transition phases, you see a clear hysteresis that is produced at high temperature, and similarly at low temperature you can see another hysteresis proceeding here. So, this is the way the stress strain curve applies for nitinol in the high temperature and low temperature regime. Plus you also have the transition which is very clearly seen, transition from the martensite to austenite phase is clearly seen in this regime, and this is also reversible, which is highly selective. So, you can clearly make out the difference between the austenite to martensite transformation, which gives you the allowance to play with the different applications depending on whether it is needed in high temperature phase or in low temperature. Now, we need to understand how this deformation works, and this is another useful article that came out in 2007 in Advanced Materials published by Mehta and co-workers. When you try to deploy the stents in cardiovascular devices, you need to see how the deformation and fracture occurs in nitinol stents, and this can be done using in situ synchrotron X-ray microdiffraction that clearly tells you the sort of transformation that happens when pressure is employed. So, this is one study which is useful to understand how the transformation occurs inside the heart when you are applying pressure, and this view graph gives the mapping. For example, before deployment when the stent is actually placed, this is the mapping which shows how the tensile strength is. The red color indicates the tensile strength, whereas the blue color in this contour explains the compressive strain. And if you see here, this the maximum local strain in austenite can vary between minus 1.5% to plus 1.5%. So, before deployment you can see the compressive strain and the tensile strain which is mapped in this extreme, and you also have a neutral axis here. Now, if you start deploying the stent, you can see how the transformation occurs. At 1 millimeter you do not see much of changes, but when you go to 2 millimeters and then 3 millimeters and 5 and 6 millimeter, you can clearly see the change between the compressive strain and the tensile strain. And especially when you are deploying the stent beyond 3 millimeter and go all the way up to 6 millimeter, you can see there is a complete transformation of your austenite to martensite. Okay. So, we can clearly map what sort of phase transformation is occurring when you are applying pressure inside your cardiovascular system. So, this is a useful way to understand how much of loading this stent can take and how much centimeter that you can deploy the strength and what is the risk factor involved. Beyond a particular condition, it cannot be brought back to its original state. In other words, it loses its super elasticity. Therefore, this contour gives you a idea about the transformation limit that is happening and that is what is mentioned here. However, it is observed even at 6 millimeter deformation, there is a region of strain stabilized retained austenite along the center of the strut that resists transformation. Consequently, the martensite transformation front moves down along the strut edge as deformation strain increases. This is what we see here. Nitinol is not the only player, there are several other ones, especially in stent applications. We have many alloys which find usefulness in cardiovascular biomedical applications. For example, platinum chromium is one alloy which is now being used. Now, the first question that might arise to us is why nitinol is replaced. Nitinol is replaced because it is of great demand, because of its application in aerospace. It is highly expensive. So, one can go for alternate ones with better features. Now, if you look at the market of stent technology in 2003, nitinol was very popular, but now you would see there are other alloys which are performing doing the same performance and they are costing much less. One is platinum chromium alloy and the other one is stainless steel alloy and the other one is cobalt chromium alloy. All these are being presently used in human heart. Therefore, it is good to take a look at what these compositions are and how they vary from each other. Now, we should also understand that merely getting a cheaper alloy is not important. We need to know whether it can really satisfy all the conditions that are needed when you put that in the coronary artery. So, when you take a platinum chromium, when you say platinum chromium stent, then you are talking about platinum 33%, chromium 18%, but still you have a larger proportion of iron in this stent. Okay. Similarly, when you say stainless steel, the greater proportion here is iron, whereas you still have chromium and nickel involved. So, it does not really go by the nomenclature, but principally the shape memory effect is actually coming from this alloy composition. Cobalt chromium is one of the most widely used now in especially in India, lot of application based on cobalt chromium, and here cobalt is maximum 52% and chromium is 20%, and then you would also see lot of other metals are being used. And there is another driver stent which is also from another company where they use 34% and 20%, and more of nickel is used, but still this is also referred to as cobalt chromium alloy. Apart from nitinol, we have several other shape memory alloys which can also do the job. Now when we think about stent, for example, as a useful application, why we are looking for different kind of alloys, why we need to drag many issues into this stent technology. One is the design pattern. These are very thin wires of the order of 2-3 millimeter, and they have to be deployed. Therefore, the stent pattern becomes very important, because stent pattern can also relieve the anginal problem to a greater extent, or it can complicate the matter once it is put inside the artery. Now these are several patterns which have emerged from different companies. You can see one is like a zebra crossing, this is one such stuff, and then you have several models. These are all a real marvel of mechanical design. It is not just to construct these models in using a CAD CAM, but then to execute this is a mechanical proficiency. So it is not just the chemistry that is important in choosing the material, but it goes all the way into a technology where you need to transcend beyond this, but keeping in effect the properties of the material and try to design several stuff. One issue that is very important is the strut thickness. Strut thickness is nothing but the gauge. Usually when we talk about a wire, we call about gauge. Gauge is nothing but the thickness. So strut thickness means thinner it is better, because if it is thicker, what will happen, it is rubbing with the walls of your artery walls, and it is constantly in contact with your lumen flow. Therefore thinner it is better, otherwise if it is thicker it is going to create more damage to the walls of your artery. So strut thickness is important, and if you carefully look at it, look at platinum chromium, look at cobalt chromium, and make a comparison with the stainless steel, you can clearly see that stainless steel ones are actually more thicker, and therefore it is not very it is not easy to bring down the strut thickness, because that is the property of this material. So in case of platinum, you can go down to 0.081 millimeters, which means you can make a very thin stent, and those are also easily deployable. So the different sort of alloys have the privilege of controlling the size. We will continue with the other information. So the strut thickness plays a very important role in deciding which sort of alloy can be widely used. Reduction in strut thickness therefore can improve the stent deliverability and improved procedural outcome and decreased rate of subsequent restenosis. We will come to this in the next few slides and show how these things can be controlled. So when you think about a stent alloy, there are 4 things that we need to have in mind. One is visibility. Visibility is nothing but as the cardiologist is trying to deploy the stent in the particular place of blockage, he needs to see it visibly so that he can easily position the stent in the right place. And this need not be done with the dye, because usually during the angiogram you try to pump it with dye to see where the blockage is, but when you are actually employing the stent, the patient may be running at risk if you are going to take so much time. Therefore, you need to quickly place the stent. Even without the help of a dye, you should be able to map whether you are in the right place. So, I will show this in one of the cartoons. So, visibility is important stuff. As I told you, thin struts can bring down side branch compromise, because when you actually are going to deploy this in a side branch, you should know whether it is going to damage the other wall. So, that will help us, and also bring down the instant restenosis risk and increase the flexibility, radial strength, which is indirectly dependent on the stent geometry, and low recoil. It should not, once you position it and deploy it, you should not recoil back, which is disastrous. Therefore, all these are very important when you are choosing the stent alloy, and these are all some of the prime factors that you would look for when you are applying. Here is 2 groups of stent. Element stent, which is actually a platinum based stent, and Liberty stent is nothing but a stainless steel based stent. This is stainless steel and this is platinum based stent. Now, if you see here, the element visibility is much better in the element stent because of the presence of platinum, whereas the Liberty stent is predominantly a stainless steel stent, and you can see for a physician he would rather go with element stent, mainly because without the dye he can easily map it. In other words, these are the X-ray images taken when the stent is deployed inside the heart. So, the visibility, element visibility plays a very important role when you are looking at a proper alloy. So, whether it is a 2 millimeter diameter or 4 millimeter diameter, we see proportionally the visibility is much more pronounced in platinum alloys. This is another real time image which was taken while the stent is actually placed. Here in the coronary artery they have placed one element stent and one Liberty stent. You can clearly see that the Liberty stent is not to be seen at all. It is not easy to map it, whereas even without a dye you can see the element stent is traceable, you can easily see the position. But during contrast, when you pump it with dye, you can see that the flow is restored irrespective of which alloy was used. But for a physician to take the right decision while he is deploying the stent, what he looks for is the visibility. So, when he takes a random X-ray photograph, he should be able to see that this is in the right place. So, but people have also used many other coatings on these devices. For example, gold coated devices have been tried, but it looks to be, although gold is a safer metal, biocompatible, it seems to be that the restenosis is appearing at a higher rate when it is gold coated. So, gold coating is actually not prevalent these days, especially on this stent alloys. Here is another example where you can see the visibility factor, and not only visibility factor, you can see actually the stent is placed here, and you can see the visibility of the stent very clearly here. And why it is important is this is done in the branching area, therefore, it has to be, it is very sensitive that it should not actually rupture this this junction. So, the choice of your stent is very important. In other words, you have to use a thin strut instead of a thick strut, otherwise it will induce more loading at this interface, which may be detrimental for the patient. Also it is found that cobalt chromium alloy, although it has higher elastic properties and it is associated with greater recoil strength, it is because of its recoil property, it is clinically a bit disadvantageous when you compare to platinum chromium stent. Here is another view graph, a real time view graph of angioplasty, where you can see this is the region where there is a blockage in the heart, and how the platinum alloy has been used to map even without contrast. This is with contrast after the stent is deployed. So you can see a normal flow of blood, but you can see the obstruction very clearly. It is a very severely obstructed patient, and one can find out that even without the biomarkers you can easily map the deployment of the stent here. And similarly a side branch is preserved. In this case you can see the blockage is here, and very carefully, because this side branching is very intricate. So if you are going to employ, you should not rupture this branch, and you can see using Taxis element, which is nothing but your platinum chromium alloy. Using that you can do the side branch preservation. The ideal stent is therefore typically considered to be highly deliverable with a thin strut, low profile, flexible design, and radiopacity. Radiopacity is nothing but visibility, because it should give the contrast when you put it under X-ray machine, and high radial strength and minimum recoil. Therefore close collaboration is needed between the engineers and cardiologists to advance this technology. So depending on the demands of a cardiologist, the technologist should be able to remap the alloy composition and give the best. So in essence, when you look at a stent geometry, the whole thing is about the material that you are choosing, which alloy you are choosing, and you can clearly see this tip. For example, this tip design is a marvel, which is a mechanical prudency. Why this tip is used? Because it will restrain the recoil of the stent, and that is actually done using lot of simulations. When you go for short segments for improved conformability and minimal gaps on a bend, you need a design like this, because when you are trying to flip it, you should not see that the strut to strut contact is made. So because you are actually mapping it through several regions, therefore when bending occurs you should make sure that there is no contact between, and only this sort of a helical contour will help you. And we also see this two connector design here, which is engineered for maximum flexibility and conformance to the vessel. So the design of the stent and the choice of the alloy goes hand in hand. Therefore the property of your shape memory alloy is very essential. The next example that I want to touch upon is shape memory polymers. From the engineering aspect, tailoring the material properties of polymers is much more easier than alloys, mainly because of the cost. Both it is the processing cost as well as the cost of the material. Polymers are much more advantageous because you can go for wide range of application, and it is traditionally much lower. Therefore shape memory polymers, which is also abbreviated as SMP, shape memory polymers, are of equal demand. Shape memory polymers can be restored with a external stimuli like light, and either you can use UV or infrared light to reverse it back, or you can use chemical effects, solvent or pH change to revert it back, or heat, and these are very easy and accessible for us to bring about the shape memory. the first person who actually used shape or who found this shape memory effect in polymer is Professor Hayashi, and he used polyurethane as the material to find this shape memory effect. And later Jet Propulsion Lab in USA, they brought out many such applications using this polyurethane, especially making open cell foams and space mission foams, biomedical applications. All this they tried to evaluate using this polyurethane. So, when you think about polymers with shape memory effect, predominantly they are polyurethane based. Okay. One or two examples that I will give. Suppose you have a polyurethane fiber and you twist it like a ring or like a spiral ring like this. Now you can straighten it out. So this is a straightened polymer, either because of application of temperature or you pulled it. Now you can actually insert this same tube in a syringe and then you can put it inside a jellyfish, okay, and then you can actually so you can see the morphology of this wire, it is a straightened one, but you can actually recover it back from the jellyfish. Once you recover it back, it again goes back to its original. Why we are doing this on jellyfish? Because you can try to simulate such applications in when we try to deal with our cell tissues. So this polymers can become very useful in biomedical applications. And what is the mechanism? Unlike the case of alloys, where in high temperature they may be hard, in low temperature it may be soft. In case of thermo responsive polymers, you have both the transition segment and elastic segment available both in the cold phase as well as in the high temperature phase. So this is exactly a opposite phenomena of shape memory alloys, because in austenite it may be hard, in martensite it may be softer in case of shape memory alloys, but in this case both the phases are present either in the cold phase or in the hot phase. As a result, you can see this is the morphology with which you start, and then you can, when you heat it, you can stretch this polymer along, and immediately when you cool it can actually retain this memory, and once you heat it again it can revert back to its original shape. So it has both the features in it. You can retain the memory when it is hot and you leave it there, or you can heat it again and revert it back. So this is one application. Also the shape memory alloys, you can try to pattern it using laser, because in this way when you try to pattern it you can try to fill this shape memory alloys with anything that you want to cap it with. So it is very useful in cell culture and in several other applications. These polymers can be easily patterned, it is not possible with shape memory alloys. So polymers can be used for making devices. This is another application of a shape memory alloy. This is nothing but a polyurethane alloy with the black composite using carbon black, and what we are doing now is putting some amount of nickel here, and this nickel you can actually apply parallelly some magnetic field, and you can alloy this nickel into straight chains like this, and a close look at it you can see nickel actually forms a chain. Why? Because once it forms a chain like this, then when you are heating this polymer, this can provide a electrical pathway, thereby you can heat this. So this whole composite becomes very conducting when you try to impregnate this with the nickel, and you can try to make this sort of linear chains of nickel inside the polymer. So this shape, I will give an example of this in a hybrid situation, how this sort of alignment can help. Here again there is another example of a shape memory effect, where you actually do indentation. In other words, you try to apply very high stress, and in this region you can see a dent is formed. This is before indentation, that means you are applying very high pressure, so it has made a mark, but once you heat it, it recovers the shape. So this is the depth of your indentation. You can actually go minus 60 nanometer, you can just plunge it with a pressure, and then once you heat it back, it again comes back to the same shape. So, the shape memory polymer incidentally can bring back the shape that you are looking for. This is one other application, and here again you can see this is a shape memory polymer. This is before you start putting it in hot water. If you immerse this in hot water, you can see slowly it changes, it bends, and then once you try to take it out, it again retains back to the same shape. So, this also has a shape memory effect upon immersing in hot water. This is another demonstration of how a hybrid polymer can be used. This is a hybrid polymer, shape memory hybrid polymer, which is used, and now we can start heating this polymer, and you can see here as you heat the cycle, slowly there is bending and it is actually touching a elastic beam. This is elastic beam, this is a shape memory hybrid. Now from here it almost comes in full contact with the elastic beam here at 80 degrees C, and on cooling again you can see that it reverts back to its original position. So, this sort of things can be used for several applications, because you can reverse and bend the shape by changing the temperature. Here again you can see the way the cyclic loading occurs when you use a shape memory hybrid. You can try to bend it any way and you can try to again retain back the same shape. This is a rubber like stuff. This is another good example where you are having a shape memory alloy and you have a shape memory hybrid material, which is nothing but your white stuff, which is a polymer, and inside the polymer you are actually having a shape memory alloy. Now what you are doing is just intentionally you break this hybrid material in B1, you are breaking it and it is now cracked here, and inside is your shape memory alloy. So what you start doing, you connect this to some piece and start applying some current, you can actually fuse the shape memory alloy, because that is also elongated. Now after you heat it, you can see it has restored back to its original position. What has happened? The shape memory hybrid also has got fused along with the healing. Self healing has happened to the shape memory alloy. Not only that, the sample is also healed. After this you can see that you can still bend it, it has recovered back to its shape. So this is a hybrid device of both shape memory alloy and a shape memory hybrid together, performing several useful applications. So in essence I have shown you some examples of alloy composites or polymer composites. In combination or separately, they find very useful applications. There are several applications which I have not covered, especially in the aerospace industry. In the next few lectures I will give you some of the bibliography where you can actually go and do further reading to enhance our understanding on this shape memory alloys.